Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 4, Section 1, Chapter 6, Topic 2, Part 2. Root causes and failure mechanisms. The root causes of semiconductor package fracture failures can be attributed to various factors.
Material properties. Inadequate material properties, such as low fracture toughness, high coefficient of thermal expansion, CTE, or poor adhesion strength, can predispose packages to fracture failures.
Design flaws.
Design issues, such as inadequate reinforcement, sharp corners, or stress concentration features, can promote crack initiation and propagation in semiconductor packages. Manufacturing defects. Process-related defects, including voids, inclusions, porosity, or incomplete bonding, can act as stress concentrators and initiation sites for fractures in semiconductor packages.
Environmental factors.
Exposure to harsh environmental conditions, such as temperature cycling, moisture ingress, or chemical exposure, can accelerate material degradation and promote fracture failures. Mechanical stresses. Mechanical loading, including bending, torsion, vibration, or mishandling during assembly or operation, can induce tensile, compressive, or shear stresses that exceed the material strength and lead to fractures.
Mitigation strategies. To mitigate semiconductor package fracture failures, several strategies can be implemented.
Material selection. Choose packaging materials with appropriate mechanical properties, such as high fracture toughness, low CTE, and good adhesion, to enhance package reliability and durability.
Design optimization. Redesign package layouts, geometries, and structures to minimize stress concentrations, improve load distribution, and enhance fracture resistance. Process control. Implement quality control measures to reduce manufacturing defects, such as voids, inclusions, or bonding defects, and ensure consistent material properties and performance. Environmental protection. Encapsulate semiconductor packages with protective coatings, conformal coatings, or hermetic seals to shield them from environmental hazards and prevent moisture ingress or chemical exposure. Packaging techniques. Utilize advanced packaging techniques, such as underfilling, encapsulation, or reinforcement, to enhance mechanical robustness, improve adhesion, and prevent crack propagation. Reliability testing. Conduct rigorous reliability testing, including thermal cycling, mechanical shock, vibration, and environmental exposure tests, to identify weak points, assess package performance, and validate mitigation strategies. Conclusion. Semiconductor package fracture failures pose significant challenges to the reliability and performance of electronic devices. By categorizing fracture modes, analyzing examples, understanding root causes, and implementing mitigation strategies, engineers can improve package design, manufacturing processes, and reliability testing to enhance durability and longevity. Continued research and development in materials, design methodologies, and reliability assessment techniques will further advance semiconductor packaging technology and ensure the continued advancement and innovation of electronic devices. Thanks for watching. Please like, share, and subscribe.